looking at stomata, leaf peel slides and the potometer to measure transpiration. Movement in and out of leaves. Leaves carry out photosynthesis efficiently as they are adapted to absorb carbon dioxide and light. Leaves are flattened, they have a large surface area to absorb carbon dioxide efficiently. Their surface area is increased further by internal air spaces. Molecules of carbon dioxide diffuse into the leaf through tiny pores called stomata. It then diffuses through the air spaces within the leaf to reach photosynthesizing cells. So here is a cross-section of the leaf, which we did last time. So just a quick recap, there's a waxy cuticle at the top. You've then got an upper epidermis, which lets the light through. Palisade cells, which contain many chloroplasts for photosynthesis. Spongy mesophyll layer, and in between those cells there are air spaces. There are vascular bundles with xylem and phloem. And then on the lower epidermis, you have, every so often, you have guard cells which surround the stomata or stoma, singular. So here is a microscope slide of some stomata. So you can see the guard cells here, which are surrounding the hole, which is the stomata. So those little pores there are the stomata, and those that are the cells that are surrounding the stomata are the guard cells. And I think this is a scanning electron micrograph of stomata, so like a 3D version. So the underside of the leaf, the lower epidermis, has many pores called stomata, and the reason they're found on the lower epidermis is because it's more protected on the lower side of a leaf from wind, from light, or anything that might cause water to evaporate, because the plant doesn't want to lose water. So you can investigate the distribution of stomata and guard cells. So the method you would use is you would paint the surface of the leaf with clear nail varnish, allow it to dry, peel off the nail varnish with forceps, place on a dry microscope slide and examine. So to record the distribution, the density of stomata on a leaf is recorded per unit area, which is usually the number per square millimetre. So a microscope is calibrated so that its field of view is known, and then you can calculate the area. So in the illustration, the diameter of the field of view of the microscope is 0.4 millimetres, so its area can be calculated using the formula pi r squared, which is the formula for an area for a circle. So pi is 3.14 and r is the radius of the field of view, which is half the diameter. So if the diameter of the field of view is 0.4, the radius would be 0.2. So to find the area, you do pi, which is 3.14, times 0.2 times 0.2, which equals 0.13 millimetres squared. So now you've got your area of your field of view. You then count how many there are in the field of view. So here there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 in that field of view. The area of the field of view is 0.13. So to find out how many there are in 1 millimetre squared, the density of stomata is therefore 92 stomata per millimetre squared. So a worked example using the same microscope. What is the density of stomata per millimetre squared based on the following counts? So you'd have to find the average of these. So the average count would be 25. And the field of view is still 0.13. So the number of stomata in 1 millimetre squared is 192 per millimetre squared. Okay, and we also need to be able to find the area of a leaf. So the easiest way to do this is you would lay the leaf on a piece of graph paper and then draw around it. Anything that is more than half a square full of the leaf is counted. Anything that's less than half a square full wouldn't be counted. So this one here is more than half. so that one would be counted. This one's less than half, so you don't count that one. And obviously all the full squares are counted. So the area of this one, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So the area of the leaf is 24 centimetres squared. So now looking at xylem vessels. So xylem vessels transport water and mineral ions, and they are made from dead cells where the end walls have broken down to form a hollow tube. And the walls are strengthened by a substance called lignin. And xylem vessels carry water and mineral ions up to the plant from the roots to the stem and then the leaves. And the movement of water from the roots through the xylem and out of the leaves is called a transpiration stream. So transpiration is where plants lose water from the surface of the leaves. Most of it is lost via transpiration or evaporation through the stomata. And the amount of water lost by transpiration increases in hot, dry and windy conditions, which are also the best conditions to dry your washing in. So as water is lost from the leaves, more water is absorbed in the roots, and as the water leaves the leaves, is lost from the leaves, water is then pulled up from the xylem to replace that water lost, and then to replace the water lost in the stem, more water is taken up through the roots, and so on. So that is called the transpiration stream. It's a continuous process, so water evaporates from the leaf, water then replaces it, carries up from the roots, the stem, into the stem, in the xylem vessels, and then to replace that water loss, water enters the root hairs in the roots. So the conditions that make your washing dry really fast, so warm, dry, windy, are also the conditions that make transpiration faster. So cutting down on water loss. So when transpiration rates increase, the roots may not be able to absorb enough water from the soil to replace the water lost at the leaf surface. When this happens, the plant then wilts. So to prevent the plant from wilting, plants can close their stomata to reduce the rate of transpiration. So the guard cells, which surround the stomata, can either open or close depending on whether the plant needs more to retain the water or whether it can open the stomata for photosynthesis. The potometer. Potometer measures the rate at which a plant takes up water. So as plants lose water by transpiration, more water is taken up, making the air bubble move along the capillary tube. The rates of transpiration in different conditions can be compared by measuring how fast the air bubble moves. So what you have is a cut of a shoot of a plant with leaves on. You would do all this underwater to prevent air entering the equipment. So you'd also have a bit of Vaseline here to keep it watertight. So this is full of water. You've got a water reservoir which you can use to reset the bubble back to zero. So at the beginning of the experiment, you'd set the bubble back to zero, and then you'd blow a fan or some wind at the chute, and as water evaporates from the leaves, the stem will take up more water, and therefore it'll cause water to be drawn in, and the bubble therefore will move this way. And you can do it over a certain amount of time so that you can calculate the rate of transpiration. So if you did it over 1 minute and it moved 5 centimetres, the rate would be 5 centimetres per minute. And you can compare different conditions. So you would have a ruler here so you can measure the distance the bubble travels in a certain amount of time. So here's an example of still air, how much the bubble moved. And then an example of windy air, so the rate of transpiration is a lot faster in windy conditions. And you can measure the rate by doing the distance moved over time, so 18 over 10 for that one, and then 7.5 over 10 for that one.